Okay. And then I know some of you like chats, so I'm going to leave the chats up. All right. Okay, so we're going to dive into chapter 7. First thing we're going to talk about is estimating the mean when we know the sigma. You can go through your focus points at your own leisure. Basically just tells you what we're going to go through and do. Because of time and money constraints, difficulty in finding population members, and so forth, we usually do not have access to all measurements of an entire population. Instead, we rely on information from a sample. In this section, we develop techniques for estimating the population mean using sample data. And then we'll list some of the basic assumptions. What do you think a potentially good source for a large number of data could come from, but may or may not be a source that researchers are typically using? It has been used in the past. I don't know if they still use it. You guys think of a large number of people that kind of have to do sort of whatever anyone tells them to do. And don't say high school students. It's not the answer. Nobody? When you say assistant, what? Oh, yes, an assistant is someone that has to do whatever is pretty much asked of them. That was very good. No. So prisons are filled with a slew of individuals, right? So in the past, we have had some psych studies done using inmates as the subjects, but then you run into different problems where, like, someone from the logical side says something like, well, how can we really all be compared to inmates? But I mean, I think it really comes down to what is being studied. I mean, just because somebody made some bad choices in their life doesn't mean that you can't also have similarities with them. So I don't know if they still use it, if they still use that subset as much as I would, because, for the most part, they're probably pretty bored and they could definitely fill out a survey. But um, there have been studies done using prisons, and that would make sense because you have a very nice large population size that you can use, right? All right, here are our assumptions that we make about the random variable x. We have a simple random sample size of n drawn from a population of x values. The value of sigma is the population standard of x is known. If x's distribution is normal, then our methods for work for any sample size n. And if x is an unknown distribution, then we require a sample size of n, or n being 30 or greater. It does say here, however, if the x distribution is distinctly skewed and definitely not mound shaped, then we need a larger sample size, like 50, 100, or even higher. Okay. All right. An estimate of a population parameter given by a single number is called a point estimate for the parameter. It will come as no great surprise that we use x bar as the point estimate for the population mean. You can see that's written there as a definition. Don't know why they gave it to you twice. Even with a large random sample, the value of x bar is usually not exactly equal to the population mean. The margin of error is the magnitude of the difference between the sample point estimate and the true population parameter value. Okay. These are definitely the chapters that I feel really bad for you guys because I think I've told you in the past, I don't typically use the PowerPoints when I'm in person. I typically walk you through the chapter and then we do a whole bunch of problems together. But unfortunately, I think going through the textbook like this would be just as boring. So at least this is kind of cut down for us a little bit. Go ahead and you can see the definition again for margin of error. I don't know why they're giving you stuff twice, so we're probably going to go through this a little bit quicker than normal. We cannot say exactly how close x bar is to mean when mean is unknown. Therefore, the exact margin of error is unknown. So we do not need to estimate it unless we, I guess, really want to. So let us continue. Right. First, we need to learn about the confidence levels. The reliability of an estimate will be measured by the confidence level. Suppose we want a confidence level of C. And if you look at the figure they give you, you can see that. Theoretically, we can choose C to be any value between 0 and 1, but usually C is equal to a number such as 0.9, 0.95, or 0.99. Those, of course, are your most popular and most well-known confidence levels, standing for, of course, 90%, 95, and 99%. In each case, the value Z sub C is the number such that the area under the standard curve is falling between negative ZC and positive. Z sub C is often referred to as the critical value for a confidence level of C. So if you thought after the exam on Monday that you would never see a Z-score again, you would be sadly mistaken. I'm very sorry for you. You just now get to apply them to different problems. Okay. The area under the normal curve from negative Z C is the probability that the standard normal variable Z lies in that interval. So here you can take a look at what that means symbolically. Okay. All right, let us use table 5 of appendix 2. That table exists in your digital as well. You just go over to the contents and then you'll see appendix. Just click on it and then you can get to the tables that they need you to use. I recommend either printing it out or just finding one that you can use off of Google. I don't believe that the program is so specific that you have to use the one out of the textbook, but then again, we all know the program is ridiculously finicky. So if you find yourself having some errors in the homework, maybe switch to the textbook. All right. This says find the number Z sub 0.99 such that 90% of the area under the standard normal curve lies between negative 0.99 and 0.99. That is, we find blah. Okay. So it's going to be where we are looking at. Here you go. So you'll have the remaining 1% split. Okay. Here you can see the corresponding area in the left tail, and they give it to you how they found it out. You guys should know how to do this just logically based on your algebra skills. All right, if you use the appendix table, you're looking for a z-score of negative 2.58, but you were looking for the closest thing to 0.0050, okay? And you get that from where? Right here, okay? So negative 2.58 and 2.58 is where you're going to find 99% of the data, right? did they really need to break it down that much for you? Not really, because you would have known that if they wanted 99% of the data, that you would have 1% left unaccounted for. Okay. And then you split that in half. All right. Optional. This is just some higher math going through and kind of telling you what the symbols are. You don't really need that. If you want to come back to the video and write it down for your own mathematical pleasures, you may do so. I'm not going to require you to know it. If you should need to know it, I would just write down the formulas and have it for your exam. But you're going to end up knowing it anyway based on all your homework. Okay. The margin of error or absolute error using X bar as a point estimate for mean. Here you go. They're giving it to you a third time in the same set of slides. However, equation 1 allows us to compute an error tolerance E that serves as a bound on the margin of error using a C% level of confidence. So you don't really need to know that X bar is what they're telling you here. Okay. Which you may not always know it. So that is a great formula for you to have. All right, note, formula 5 for E is based on the fact that the sampling distribution X bar is exactly normal, which means mu and standard deviation would also be normal. This occurs whenever the X distribution is normal with a mean and standard deviation. If the X distribution is not normal, then according to the central limit theorem, we need N to be 30 or greater. You guys know all of this at this point. All right. Using equations 1 and 5, we conclude the following. Okay. Equation 6 states that the probability is C, that the difference between X bar and mu is no more than the maximal tolerance E. So if you do some algebra, you find the following. All right. Again, you're going to end up working with all this in your homework. So if you need to come back to this to write it all down, you certainly may, but I feel like you will be fine. Okay. All right. For mu, we can rewrite it in the following mathematical equivalent way. All right, so there's 8. Since formulas 7 and 8 are mathematically equivalent, the probabilities are the same. Therefore, 6, 7, and 8, we obtain the following for 9. Please let me know if you need more time for this stuff. Again, I think you'll just end up working it out in your homework. Okay, equation 9 states that there is a chance C that the interval from X bar minus E to X bar plus E contains the population mean mu. We call this interval a confidence interval for mu. All right. Okay. Here's your procedure. I'm not going to read it for you. You may read and write down what you feel you need to write down. You will have to do this a ton in your homework and your quiz, or in your quiz, yeah. It will end up becoming old hat to you. All right, let's look at this example. Julia enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained consistently good. Usually she jogs 2 miles per day. The standard deviation of her time is 1.8 minutes. During the past year, Julia recorded her times to run 2 miles. She has a random sample of 90 of these times. Wow. Wow, that's a lot of mileage in a year. For these 90 times, the mean was X bar equals 15.60 minutes. Let mu be the mean jogging time for the entire distribution of Julia's 2-mile running times taken over the past year. Find a 95% confidence interval. So, requirements. Do we have a sample size larger than 30? That would be a yes, because she did it for 90 times. All right. We also know what sigma is, because they gave it to us. So we can figure this problem out. All right. To compute E for 95% confidence, we need to use Z sub C equal to 1.96. Here's your 90%. Or sorry, 95%, 1.96. All right. Plug everything in. They chose to use equation 10. You could have tried using another one. I mean, but I think you should just go with what you know. And if that's the easiest way to get you to certain things, then that's what you should do. You could have known that this is what E is. And so everywhere you had an E, you could have replaced it with that. But why do that when you can just do this? Right? Oops. Super fast. All right. So then they found their interval. We conclude that 95% confidence that the interval from 15.23 minutes to 15.97 minutes is one that contains the population mean for jogging times for Julia. Any questions on what they did and how they found it? Ah, there it is. Okay. Good deal. All right. Sample size for estimating the mean. All right. Again, I'm not going to read everything to you. So it's always a good idea for you to have a large sample size when possible. Number one, it lets you be able to do certain statistics like this. Number two, if you have a large sample size, then you're not going to get a lot of critics saying, well, obviously you have a small sample size, so of course you're going to find what you need to find. The bigger the sample size, the more data you have, the less critiques you're going to end up getting. How to find the sample size and for estimating mu when sigma is known. Okay, so when you need to figure out what sample size you should do for something, or you should have, or you can verify that someone else had, here's your information. All right. This works if the distribution of the sample mean X bar is approximately normal. So you have to be told that in the problem. All right. A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. A preliminary study of a random sample of 50 salmon showed S approximately 2.15 pounds. How large a sample should be taken to be 99% confident that the sample mean is within 0.2 pounds of the true weight of mu? Okay, so this Z 0.99 equals to 258. We already found that earlier in the slides, but you can find it in the table. E is given to us. The N, the sample size is given to us, and then the sigma is given to us. Okay. So we're going to use equation 6. We're going to find for the N that would include not with 99% confidence. So in determining the sample size, any fractional value of n is always rounded to the next highest whole number. Obviously, we know that we're not going to have 0.2 tenths of a fish unless, I guess, a bear got to it first and you only had a head left. We conclude that the sample size of 770 would be large enough to satisfy the specifications. Of course, a sample size larger than 770 would also work. All right. You will have questions like this, so be prepared to answer them. Okay. All right. That is the end of section 7.1. Anyone having any questions for me on it? Okay. Estimating mean when sigma is unknown. Is that not what we just did? Oh, I guess we did it when it was known. Very confusing titles. Okay. We're going to learn about t-distributions, using degrees of freedom and confidence intervals or levels, and compute confidence intervals for mean when sigma is unknown. All right. In order to use the normal distribution to find confidence intervals for a population, we need to know the value of sigma. Okay. However, much of the time when mu is unknown, sigma can be unknown as well. In such cases, we use a sample standard deviation S to approximate sigma. When we use S to approximate sigma, the sampling distribution for X bar follows a new distribution called a student's T distribution. Honestly, I've never heard it referred to as students, but I have heard of T distributions, so that's interesting. Students' T distributions were discovered in 1908 by Gosset. He was employed as a statistician by Guinness Brewing Company, a company that discouraged publication of research by its employees. As a result, Gosset published his research under the pseudonym Student. Gosset was the first to recognize the importance of developing statistical methods for obtaining reliable information from samples of populations with unknown sigma. Okay. I am not going to test you on the history of this, so we're just going to dive right into it. Maybe if we were having class in person, I would throw it up as a bonus. Oh. I am so sorry. I have mad core allergies, and it is the most annoying thing on the planet during a global pandemic. It's very annoying. Okay, so here's how we find the T distribution. We have X bar minus mean, or mu, over S divided by the square root of N. And then with the T distribution, we have degrees of freedom where we find that by taking N minus 1. If many random samples of size N are drawn, then we get many T values from this equation. These T values can be organized into a frequency table and a histogram can be drawn, thereby giving us an idea of the shape of the distribution. T distribution, mind you, for a given N. Fortunately, all this work is not necessary because mathematical theorems can be used to obtain a formula for the T distribution. However, it is important to observe that these theorems say that the shape of the T distribution depends only on N, provided that the basic variable X has a normal distribution. So here's your big bell ringer for the day. When we use a T distribution, we will assume that the X distribution is normal. Okay. Degrees of freedom, if you haven't figured that out by now, it's N minus 1. So no matter what the N is that they give you or that you find, you subtract 1, and that gives you degrees of freedom. Okay, you will have to use this. It will be in the table. The main observable difference between the t distribution and the standard normal z distribution is that the t distribution has somewhat thicker tails. Okay, thicker in the sense that you're not going to get your typical 1% down there. Okay, it might be a little bit higher. All right, this shows a difference for you. Questions on that? I am not sure if you will have to make a t distribution or if you'll just have to answer questions with it and find them and that kind of thing. The homework may have you do it. I doubt that the quiz does, and I really don't know if there's going to be anything like that on the exam. All right. Here's your properties. Again, the distribution is symmetric about the mean. The distribution depends on the degrees of freedom. The distribution is bell-shaped but has a thicker tail. As the degrees of freedom increase, the distribution approaches the normal distribution, and the area under the entire curve, of course, is 1. Okay. Using table 6 to find critical values for confidence intervals. All right. Again, this is in Appendix 2. Again, you should be able to find it digitally, but of course, you can also find it via Google. I do not care how many tables you use on your exam. If you prefer to use digital ones, you of course are allowed to open those. If you would like to print them out, you may use those. I would not let yourselves, though, get bogged down with a bunch of paper. I don't want anyone to be stressed out. All right. Here you can see that we have another probability. Okay. Let's just get to an example, shall we? All right, here we go. Here we need to find the critical value T sub C for 99% confidence interval for a T distribution with a sample size of N equal to 5. Why are we not going to the row that has degrees of freedom equal to 5? How do we find degrees of freedom? Yes, you would all be correct. We're going to subtract by 1, and that's why we're finding a 4 instead of a 5. Great job. Okay. First, we need to find the column heading 0.990. Next, of course, we're going to take n minus 1, so 5 minus 1, which is 4. And when we read down the column, you will find t equal to 4.604. You can use a t. A lot of times when you do this by hand, these little subparts drop off. As long as you know what you're doing, then you're going to be fine. Confidence intervals for mu when sigma is unknown. So here is a similar approach where we find this E, which is equal to T sub C times S divided by the square root of N. Here you can see they did some more algebra and rearranged it. Okay, here's your procedure. Assuming that most of you can go back and watch the video when you want, we are just going to go as quickly as we can. Okay. All right, so suppose an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horse. Reconstructions of the skeletons of 7 miniature horses show the shoulder heights in centimeters to be the following. For these sample data, the mean is X bar 46.14 and the sample standard deviation S equal to 1.19. Let mu be the mean shoulder height in centimeters for the entire species of miniature horse. Find a 99% interval for mu, the mean shoulder height of the entire population of such horses. All right, so first you have to check the requirements. We assume that the shoulder heights of the reconstructed skeletons form a random sample of shoulder heights for the miniature horses of unknown species. The X distribution is assumed to be approximately normal. Since sigma is unknown, it is approximate. It is appropriate to use the t-test or t-distribution. So 7 is our n, so degrees of freedom will be 6. And we're going to use the table. From the table, you find 3.707. So the standard deviation is 1.19. Plug it all in. There's what you get. Okay. All right. So if we interpret that, the archaeologist can be 99% confident that the interval from 45.5 centimeters to 47.8 centimeters is an interval that contains the population mean for shoulder height of this species of miniature horse. Awesome. I don't know why they're showing you this, I guess to reiterate how you find it and what it means, so you can take a look at that later if you need to. All right. There are a couple different situations with this setup. So here's situation 1, most common. You can pull that information out again later as you need to. Situation 2, of course, they are telling you that it almost never happens. So more than likely you might have some kind of homework question on it. All right, that is the end of 7.2. Anyone have any questions for me? Okay. Is on estimating P in the binomial distribution. Here are points that we will go over. Again, you can read those to yourselves. All right. The binomial distribution is completely determined by the number of trials n and the probability p of successes on a single trial. For most experiments, the number of trials is chosen in advance, then the distribution is completely determined by p. In this section, we will consider the problem of estimating p under the assumption that n has already been selected. We are employing what are called large sample methods. We will assume that the normal curve is a good approximation to the binomial distribution, and when necessary, we will use the sample estimates for the standard deviation. Empirical studies have shown that these methods are quite good and provided both n times p is greater than 5 and n times q is greater than 5, where q is equal to 1 minus p. Those little factoids down at the bottom will probably show up as a multiple choice question on either your quiz or your exam, or potentially both. So there is that. Let R be the number of successes out of n trials in a binomial experiment. We will take the sample proportion of successes p hat. equal to be R divided by N as our point estimate for P, the population proportion of successes. All right. Here are your point estimates for P and Q. Again, you read that as P hat, and it's going to be equal to R divided by N. Q hat is, of course, going to be 1 minus P hat, where N is the number of trials and R is the number of successes. So if you've ever looked at your calculator and been like, I wonder what that N and R mean next to combination and permutation, that is what they mean. Number of trials and number of successes. All right. To compute the bounds for the margin of error we need for information about the distribution, P hat is equal to R divided by N values for different samples of the same size N. All right. It turns out that for large number samples, the distribution of values is well approximated by a normal curve with mean equal to P and standard deviation sigma equal to the square root of P times Q divided by N, the whole thing divided by N. If you get confused and you don't remember what Q is, remember you can always do P times 1 minus P and the whole thing divided by N. But you guys should know what Q is at this point. Since the distribution of P hat is approximately normal, we will use features of standard deviation or standard normal distribution to find the bounds. Wow, I cannot read today. I'm going to blame it on the allergy meds, guys. Recall that Z sub C is the number such that the area equal to C under the standard normal curve falls between negative C and positive. All right. Then in terms of the language of probability, there you have it. I'm definitely not going to try to read that to you. Equation 17 says that the chance is C that the numerical difference between P hat and P is somewhere between blah and blah. With the confidence interval, our estimate P hat differs from P by no more than the error given. Okay. Again, you need to use these. You need to understand what they mean, but I don't think you need to sit here and write all of it. You're going to end up working through it if you haven't worked through it already. All right. Again, here's the optional derivation of what's going on. You don't need to really know that. All right. What you can do is if you really wanted some nice notes for your exam, you could come in and decide which one of these help you with your homework and then write them down on a sheet of paper or the note card, whichever you end up having at home. These are P hats, the little things that look like they're redacted for some weird reason. You can thank the publisher for not having the best slides there about that. Obviously, everything else showed up, so I don't know why that wouldn't. Let's see if we can get to an example, shall we? No, just more talking. Again, you can come back in the video and watch this. Here's your procedure. Right. Finally, an example. Let's return to our flu shot experiment described at the beginning of this section. I don't recall a flu shot experiment, but I'm going to guess it's in your textbook reading. Suppose that 800 students were selected at random from a student body of 20,000 and given shots to prevent a certain type of flu. Does this sound scary right now or not? All 800 students were exposed to the flu, and 600 of them did not get the flu. Let P represent the probability that the shot will be successful for any single student selected at random from the entire population of 20,000. Let Q be the probability that the shot is not successful. What is the number of trials and what is the value of R? Since each of the 800 students received the shots may be thought of as a trial, then N equals 800 and R equals 600. What are the point estimates for P and Q? We would take R divided by N and we get 0.75. So then we're gonna take, this Q should have an equal sign here. This is a very weird transition by them. P hat minus 0.75 will give you 0.25. Requirements, what would it seem that the number of trials is large enough to justify a normal approximation to the binomial? Here you go through and you prove that. 800 times 0.75 is 600, which is greater than 5. And 800 times 0.25 is 200, which is greater than 5. So a normal approximation is justified. We have to find 99% confidence interval for P. So again, you're going to use your table. You're going to plug in. There's your error. You're going to take your error away from your P hat, and then you're also going to add it to your P hat. So when you read that, it's going to be, we are 99% confidence that the probability a flu shot will be effective for a student selected at random is between 71% and 79%. Not really what I would like right now, but I guess it's better than 0. So interpreting results from a poll. So when you guys are a little bit older and you end up voting for your next president, you will probably question some things, and I don't think you'd be wrong to question them, because I don't know how much of this polling information is actually being correctly followed. Who knows? I don't know. I don't work at the polls for a reason. Newspapers frequently report that the results of an opinion poll, in articles that are given more information, a statement about the margin of error accompanies the poll results. In most polls, the margin of error is given for a 95% confidence interval. So, general interpretation of poll results, here they are. They look pretty similar to the stuff you've been working with, which is, of course, why they are included in this chapter. Sample size for estimating P. Suppose you want to specify the maximal margin of error in advance for a confidence interval for P at a given confidence level C. What sample size do you need? The answer depends on whether or not you have a preliminary estimate for the population probability of success. Okay. So here's your procedure. Again, whether you're writing it down now or you're going to come back to the video later. There it is. Okay. A company is in the business of selling wholesale popcorn to grocery stores. The company buys directly from farmers. A buyer for the company is examining a large amount of corn from a certain farmer. Before the purchase is made, the buyer wants to estimate P, the probability that the kernel will indeed pop. Suppose a random sample of N kernels is taken and R of these kernels pop. The buyer wants to be 95% sure that the point estimate P hat for P will be in the error either way by less than 0.01. If no preliminary study is made to estimate P, how large a sample should the buyer use? So in this case, we're going to go with equation 22. We come down to 95, we get 1.96. So N is equal to 1/4 Z critical Z-score over error, and we're going to square that and then do the multiplication. So the buyer would need a sample of 9,604 kernels. All right. A preliminary study showed that P was approximately 0.86. If the buyer uses the results of the preliminary study, how large of a sample should he use? So you're going to do the same thing, roughly. And now it says there should need to be a sample size of at least 4,626 kernels. All right, this sample is less than half of the sample size necessary without the preliminary study. All right. Any questions on 7.3? Estimating mu sub 1 minus mu sub 2 and p sub 1 minus p sub 2. This section's pretty easy and self-explanatory. You have to find them and then you literally just subtract. All right. Distinguish between independent and dependent samples. Here are all your different options you could have. Interpret the meaning and implication of an all positive, all negative, or mixed confidence interval. Independent samples and dependent samples. These should be very familiar to you because they are going to be similar to your independent and dependent variables. All right. How can we tell if two populations are different? One way is to compare the difference in population means or the difference in population proportions. In this section, we will use samples from two populations to create confidence intervals for the differences between population parameters. To make a statistical estimate about the difference between two population parameters, we need to have a sample from each population. Samples may be independent or dependent according to how they are selected. Okay. Two samples are independent if the samples data drawn from one population are completely unrelated to the selection of the sample data drawn from the other population. Two samples are dependent if each data value in one sample can be paired with a corresponding data value in the other sample. Data samples and data pairs occur very naturally in before and after situations in which the same object or item is measured twice. In this section, we will confine our interest to independent samples. Okay, so that means for chapter 7, you are not having to worry about dependent samples. Independent samples occur very naturally when we draw two random samples, one from the first population and one from the second. Because both samples are random samples, there is no pairing or measurements between the two populations. All the examples of this section will involve independent random samples. All right. You guys can read this later. I'm just going to work you through the examples. Here's figure 7.7. It's illustrating the sampling distribution of x bar sub 1 minus x bar sub 2. Okay. Confidence intervals. The values of x bar sub 1 minus x bar sub 2 come from repeated independent sampling populations 1 and 2. Blah, 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 blah. Here's your procedure. All right. All right, here's an example. In the summer of 1988, Yellowstone National Park had some major fires that destroyed large tracts of old timber near many famous trout streams. Fishermen were concerned about the long-term effects of fires on these streams. However, biologists claim that the new meadows that would spring up under dead trees would produce a lot more insects, which would in turn mean better fishing in the years ahead. Guide services registered with the park provided data about the daily catch for fishermen over many years. Ranger checks on the streams also provided data about the daily number of fish caught by fishermen. Yellowstone Today, a national park publication, indicates that the biologist's claim is basically correct and that Yellowstone anglers are delighted by their average increased catch. Suppose you are a biologist studying fish data from Yellowstone streams before and after the fire. Fishing reports include the number of trout caught per day per fisherman. A random sample of 167 reports from the period before the fire showed that the average catch was 5.2 trout per day. Assume that the standard deviation of daily catch per fisherman during this period was 1.9. Another random sample of 125 fishing reports 5 years after the fire showed that the average catch per day was 6.8 trouts and that the standard deviation during this period was 2.3. Again, you can go and see that you can isolate your information between first and second. I did not read it that way. They don't have to always give it to you that way. So, right. Check requirements. For each sample, what is the population? Are the samples dependent or independent? Explain. Is it appropriate to use a normal distribution? Explain that as well. So, all right, the population for the first sample is the number of trout caught per day by the fishermen before the fire. The population for the second sample is the number of trout caught per day after the fire. Both samples were random samples taken in their respective time periods. There was no effort to pair individual data values, therefore the samples can be thought of as independent. A normal distribution is appropriate. You guys can read this. I'm not going to. All right, so we have n sub 1 equal to 167, x sub 1 equal to 5.2, sigma sub 1 equal to 1.9. You can see all the rest. Critical value is 1.96. They're going to shove it all in. Rounds up to 0.50. So then you're going to go through and do your intervals. Okay. Notice how we have two negatives here. Just kind of take note of that. So what is the meaning of the confidence interval computed in part 5? We are 95% confident that the interval blah, 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 containing the population represents the population average daily catch before and after. Put it another way, since the confidence interval contains only negative values, we can be 95% sure that mu sub 1 minus mu sub 2 is less than 0. This means that we are 95% sure that mu sub 1 is less than mu sub 2. In words, we are 95% sure that the average catch before the fire was less than the average catch after the fire, which you basically could have guessed due to the information they had given you. All right. Confidence intervals for mu sub 1 minus mu sub 2 when you have unknown variables. Surprise, surprise, we're going to use the t-distribution, or at least a slightly varied form of it. Okay. It's not exactly the same as the t-distribution, but it's a good approximation. And we adjust the degrees of freedom by one of the following methods. All right. So here's procedure. Go ahead and read through it either now or later. You can always pause the video later and take all that down. Alexander Borbely is a professor at the medical school of the University of Zurich, where he is the director of sleep laboratory. Dr. Borbely and his colleagues are experts on sleep, dreams, and sleep disorders. Okay, great. He has a book. Here's what he's telling us in his book. Rapid brain waves, wakefulness, are in the range of 16 to 25 hertz. Slow brain waves, sleep, are in the range of 4 to 8 hertz. During sleep, a person goes through several cycles. Each is about 90 minutes of brain waves from rapid to slow and back to rapid. During sleep, brain waves are at their slowest. In his book, Borbely comments that alcohol is a poor sleep aid. In one study, a number of subjects were given half a liter of red wine before they went to sleep. The subjects fell asleep quickly, but not remain asleep the entire night. Toward morning between 4 and 6 a.m., they tended to wake up and have trouble getting back to sleep. Suppose that a random sample of 29 college students was randomly divided into two groups. First group was 15, and they were given half a liter of red wine before going to sleep. Second group was 14, and they were given no alcohol before going to sleep. Everyone in both groups went to sleep at 11 p.m. The average brainwave activity 4 to 6 a.m. was determined for each of the individuals in the groups. And here's the information that was given. Okay, this is group 1. You're going to use x sub 1 values. Group 2. All right, here they found the x bar and the standard deviation, the same for the second group. And you can see that we're going to go ahead and that everything meets the requirements. So again, you're going to look for the t distribution. This comes straight from the t table. You're going to plug it in to find the margin of error. Here is your confidence interval. I'll go back in case you need that for the video. All right. What is the meaning of the confidence interval from part B? So group 1, we have brainwave activity for people who drank half a liter of wine before sleeping. Group 2 represents the average brainwave activity for people who took no alcohol. Both periods were measured. We are 95% confident that the interval between 11.8 and 14.3 hertz is one that contains the difference. It would seem to be reasonable to conclude that people who drink before sleeping might wake up in the early morning hours and have trouble getting back to falling asleep. Since the interval contains positive values, we could express this by saying that we are 90% confident that u sub 1 minus mu sub 2 is positive. This means that mu sub 1 minus mu sub 2 is greater than 0. Thus, we are 90% confident that mu sub 1 is greater than mu sub 2. That is average brainwave activity for 4 to 6 a.m. for a group drinking wine was more than the average brainwave activity for a group not drinking. Oh, it goes on. Good Lord. Okay, so here's what we are going to do. All right. Estimating the difference of proportions. We conclude this section with a discussion of confidence intervals for p sub 1 minus p sub 2, the difference of the two proportions from binomial distributions. The main result on this topic is the following theorem. There's your procedure. Again, you may pause it and write it down either now or later. You can see we have binomial experiment 1 and binomial experiment 2. Confidence intervals down at the bottom. Okay. All right. And we're back to the professor at Zurich. He also has a study going on with REM sleep. Based on his study, over 650 people in the lab found that 1/3 of all the dream reports contain feelings of fear, anxiety, or aggression. There is a conjecture that if a person is in a good mood when falling asleep, the proportion of bad dreams, fear, anxiety, and aggression might be reduced. Suppose that two subgroups of subjects were randomly chosen for a sleep study. In group 1, before going to sleep, the subjects spent 1 hour watching a comedy movie. In this group, there were a total of 175 dreams recorded, of which 49 were dreams with feelings of anxiety, fear, or aggression, meaning that more of them were happy dreams or they didn't dream at all. In group 2, the subjects did not watch the movie but simply went to sleep. In this group, there were 180 dreams recorded, and 63 were feelings of anxiety, fear, or aggression. Yes, it checks. Okay, let's continue. So here we find our P hat and our Q hat. Nicely done. You can verify it because if you add them up, it'll be 1. Here's our second P hat and Q hat. All right. Since both sets are larger than 5, then the theory is appropriate. Okay. We're looking to compute a 95% confidence interval for P sub 1 minus P sub 2. Again, we're going to go back and get our critical value from the table. You guys will probably end up memorizing this table, so you won't have to keep going back and forth to it. Just make sure you memorize it correctly. That was obviously for sigma hat sub 1. Nope. It includes both. My apologies. So here you go. Gonna go through and figure it out. Now here we have a negative leading to a positive. That's gonna tell you something else, okay? We are 95% sure that the interval between negative 16.6% and 2.6% is one that contains the percentage difference of bad dreams between groups 1 and 2. Since the interval is not all negative or not all positive, then we cannot say one way or the other if it will be greater than or equal to 0. Thus, the 95% confidence level, we cannot conclude that P sub 1 is less than P sub 2 or that P sub 1 is greater than P sub 2. The comedy movies before bed help some people reduce the percentage of bad dreams, but at 95% confidence level, we cannot say the population difference is reduced. Here is your procedure for that. It does look like we're going to get done on time, which is good. Again, you can come back into the video later. I will have it posted later today, and you can pause, take notes, do whatever you need to do. Good. It is done.